Hello, my name is Stephen Beardsley. This is my project dissertation video for the Comp 390 module. This project is titled Simulated Automotive Software, or SAS for short, and fits into the ethical category of A0. The aim of this software is to create a testbed for new automotive components to be networked, integrated, and controlled within a simulated environment. This comes from a rise in digital twin solutions being adopted by larger engineering companies modeling complex systems. Digital twins are virtual copies of hardware deployed in real or simulated environments. To accomplish this goal, I will be using industry standard techniques and languages to form an effective and maintainable architecture. The simulated automotive will be controlled by a Windows desktop application called the Vehicle Simulation Platform, or VSP. This will be developed using the .NET framework employing the Model View Controller architecture. This application will allow the user to configure, deploy, control, and monitor the simulated car in real time, displaying clear and relevant feedback. The simulated automotive will be comprised of a NEON system. NEON, or Networked ECU Orchestration Nodes, is the collection of independently running network Docker containers deployed within a Linux OS. It is comprised of three subsystems: the dashboard, which acts as the network configurator and communicates with the VSP, the transmission control module, which handles events such as gear changes, and the engine control module, which handles fuel modeling, torque generation, drive forces, and a thermodynamic model within the engine. Each of these subsystems are deployed within Docker containers containing the C++ executable, a log file, and a shared configuration file. As shown in the diagram, they communicate between themselves using the CAN networking protocol, encapsulated within UDP. NEON receives commands via HTTP request from the VSP, but broadcasts its data JSON using the WebSocket protocol, which offers full duplex persistent connection between a client and server over a single TCP link. Unlike HTTP, it allows both sides to send the data at any time without repeated requests or connection overhead. This makes it ideal for the continuously changing NEON data because updates can be pushed instantly with low latency and minimal bandwidth usage. As mentioned, my subsystems will use CAN to communicate. CAN, or Controller Area Network, is the industry standard Layer 2 protocol that defines how different ECUs, electronic control units, communicate inside an automotive. It uses a central bus and a publish-subscribe model, so all data is sent around the network and components subscribe to the packets which concern them. As part of my project, I have developed an interface control document, or ICD, defining each message sent across the network, a CAN networking library implementing the behaviors mirroring how the protocol would function, and a bit parser library, which allows for the serialization and deserialization of different data types and messages. The VSP can be reached via the Windows toolbar. The first thing the user will see when opening the application is the deploy page. This page is where NEON is configured and deployed. The user is able to choose between a range of different engine and transmission types and also choose the colour of their car. When I click deploy, the deployment controller will run a bash script which creates a JSON and stores it into a configuration file, compiles the code into separate executables, creates Docker containers from custom Docker images per component, copies the configuration, log, and executable files into the containers. When this script has ran and completed, NEON is deployed and communicating with the user interface. When NEON has been deployed, the track and logging pages become visible. The track page is where NEON can be controlled and monitored, and the logging page is for debugging to see what raw data is being sent across the network from NEON. Focusing on the track page, this page features clear controls such as throttle, brake, refuel, and gear change. These send command messages via HTTP request to the NEON system. The page also features an aesthetic display showcasing the data received from NEON in real time. Controlling NEON, I can increase the throttle, subsequently increasing the RPM and speed when the car is in gear. Taking torque generation within the engine, for example, the engine produces torque following a Gaussian bell curve peaking at around 60% of the RPM range between idle and redline, then tapering off as the engine approaches its limits. Throttle input it scales this torque output directly, so flooring the pedal at peak RPM delivers maximum force to the wheels, whilst lifting off triggers engine braking at smoothly raising speeds. Warnings will also be shown in the bottom right corner for key events such as engine overheating, recommended shift patterns, low or no fuel, and if the engine stalls to something like over rev. These controls are sent to a dashboard container as HTTP requests, which are then passed into CAN messages, which are packaged into UDP packets to be broadcasted across the network. These messages are defined within an interface control document I've developed, and there are different message types, including error, command, speed control, and status. Each subsystem will subscribe to the ones which concern it. The software also features a live graphs display, showing the RPM, fuel, temperature, and speed in real time in a flyout window, visually demonstrating the simulation behavior. Stepping now into the Linux environment where Neon is deployed, we can see what subsystems are running. So here you've got the transmission, the engine, and the dashboard. And the dashboard is exposing its ports, and this is for the HTTP endpoints, which allow it to communicate with the user interface. We can also see the Docker network, which all the containers communicate over. So each container will have its own IP address, MAC address, and this allows them to communicate together. We're also able to see what the containers are logging and what they're doing, and this is derived from a C++ script, which I've developed as part of this project. So you've got timestamp, a category, and some of the messages are logged, and the telemetry data in the dashboard, for instance, is also logged. So this is the JSON which the user interface is receiving. So we're also able to step inside the containers and see what is happening. So we can see what's inside of it first of all. So it's got the executable, the dashboard executable, and the shared configuration file, and then the logs. So we can see what the configuration file contains. So this is derived from the choices when configuring the car. So we've got an engine profile and a transmission profile. And we can also see what's running. So we've got the C++ compiled binary, which is running, and this will be the same across each container in a similar structure. As part of the testing for this project, I've created comprehensive unit tests using industry standard Google test library to create effective tests for the C++ library code that I have developed. This is validated by my use of the gcov tool and a Python script to create a test coverage HTML report showing the completeness of my unit tests. I've also written a range of acceptance or system tests, something I picked up on during my industrial placements, and these tests help verify that the system behaves as expected and are crucial to software updates and ensuring a robust software solution. In order to evaluate SAS, I adopted two static analysis tools. These are tools that I've experienced with within the engineering industry and check and validate good code. Tools like ReSharper can be tuned to software programming standards, and I've tried to emulate the standards I've had previous experience with, such as DO178C, as this project includes simulated real-time embedded systems, so enforcing good standards is good practice and would be what would happen in an engineering company. The implementation of the Lives Graph page also helps show the behaviours of a simulation are sensible and correct. Some conclusions of my SAS project. Some of the future work includes making the simulation involve more systems, including implementing real hardware so it can be tested against my simulated components within the virtual environment, which goes back to the core ethos of digital twins. Some positives of the project was that the technical stack included a wide array of languages, software development tools, and architectures, which is much like what a large engineering company would aim to achieve. Some roadblocks was that without real hardware systems or specifications, I was unable to verify and validate the behaviours of my subsystems.